Friends, good morning and welcome to this lecture series of geomorphology. Today we will continue with this fluvial process, which in the last class we are discussing that the fluvial process is the most dominating geomorphic process among others. So, others geomorphic processes like this glacial, like this marine and this aeolian processes, they are confined particular domains. However, the fluvial systems, the rivers, the channels, the streams, they are well distributed throughout this globe, throughout this continental side, and they 24/7 try to modify the landscapes. So, in the last class also we are discussing about the stream generation procedures. There are two types of flows. One is called this overland flow, that is called Hortonian overland flow, another is saturated overland flow. So, the saturated overland flow, it is occurs when there is the pore spaces of the soil or this medium is totally saturated and the medium is not capable to absorb more water. So, that overland flow occurs, and due to this saturation the adhesive force among these particles that it decreases, and finally, these particles loosens and try to move due to fluid pressure. So, this is how we are getting a channel, that means water as well as sediment within the system. Similarly, we have rills, we have gullies, then we have valleys. Rills, they are the small channels, not mappable scale, but gullies, they are mappable scale, and then it is valleys. So, its size increases. So, today we will discuss about this bedrock channels, alluvial channels, channel that which are flowing through bedrocks, and how channels longitudinal profile evolves with time, with tectonics, with climate, with rock types, with like that. So, here one called bedrock channel. What do we mean by bedrock channel? Sometimes you might be noticed that whenever you go to field, suppose for example, hilly terrains or these hard rock terrains, there are channels. Throughout this channel bed you will find exposure of hard rocks, and within that channel at some stretches you will find this hard rock is completely exposed, and some channels or some stretches it is covered with alluvium like sand, silt, clay, organic matters like that. So, bedrock channels are those channels which flows through this rock exposure, that is called bedrock channel. On contrary, there is another type of channel which is called alluvial channel, and mostly the alluvial channel flows through alluvium, that is loose sediment like this alluvial channels, Ganga plain channels, they are alluvial channels. Similarly, coastal plain channels, they are alluvial channels. However, if you move to peninsular side, the channels which are flowing through hard rock exposure, these are called the bedrock channels. So, now the question arises, if it is a bedrock channel or it is a alluvial channel. So, what is its utility to geoscientists? Generally, whenever we move to field for rock specimen collections, we move along this lower part of this topographic level, so that we can get the exposure of rocks. So, generally it is a general practice of geologists, they follow these channels. So, because the channels they cut through these rocks and cut through this alluvium, and sometimes along these channels there are rock exposures are found. So, for sampling purpose, for rock sampling or rock specimen collection purpose, we move along these channels, so that there are chances that we can get the exposure, and through this exposure we can collect these rock specimens. So, during extreme flooding, jointed rocks like columnar basalt, jointed sandstone, joint rocks, that any rock which is jointed, either it is a joint is inherent property or it is later on superimposed. So, through this jointed rock, if we have some extreme flood events are there. So, due to swirling action, some of these blocks, intact blocks, they are carved out from these rocks, and this process is called clocking, or it is called clock. So, it is the either it is a columnar basalt, it may be any type of jointed rock. If we are removing a piece, removing different pieces, different blocks of rock due to swirling motion of this water due to high flood time. So, this process is called clocking. So, these inflections in the long profile of a stream are called neck point. Neck point means suppose longitudinal profile of a stream. Longitudinal profile, it is concave upward. So, this concave upward, it should be smooth like this, it should be concave upward. However, it is not as smooth as we think. So, that depends upon many factors, that depends upon the rock type through which this stream is passing through, and tectonisms. So, this faulting across this stream path, and there are dams, artificial reservoirs and dams, or natural reservoirs, natural lakes. So, all those affect this longitudinal profile of the river or the stream. So, there is subsequent evolution after an origin by these processes other than local structure that control, such as fault movement. Fault movement, if you move to peninsular rivers, even if the Ganga plain rivers, there are many subsurface and surface faults, they are influencing the longitudinal profile of this river. All those major rivers like Ganga, Yamuna, Ghagra, Kosi, if you take this longitudinal profile, it will not, though it is overall it is concave upward, but within that concavity you will find local convexity. So, here comes this story of this hill slope evolution or this slope processes we are talking during our initial classes. Okay. So, this longitudinal profile overall though it is concave upward, but within that concavity we get the convexity due to this protrusion of this fault rock types and other factors like natural or artificial lakes, reservoirs, so like that. So, such as fault movement across the channel that creates a headward migrating scarp. For example, if you see here, this is the if I take this longitudinal profile of a channel will be like this, and within that if I am getting here, suppose for example, we are getting like this, we are getting like this. So, that means these are these places, they are of geomorphic speculations, that is of geomorphic importance. Why geomorphic importance are there? Because within that convexity there are many geomorphic feature, either it is tectonic feature is involved, or this lithologic feature is involved, or other features are involved that can be solved from here. So, longitudinal profile, whole longitudinal profile is not interest for a geomorphologist. So, geomorphologists are more interested in the longitudinal where there is an exception in the longitudinal profile, where there is convexity. So, either if there is any upliftment is going on there, is there any fault movement is going on there, is there any other rock types which is not exposed, it is there. So, that means all these speculations, this comes from this longitudinal profile where there is exception. Then we are talking about bedrock channels. Here we will talk about this alluvial channels. As we know that alluvial channels, there are channels which are moving through the alluvium, completely alluvium field. So, that is why that is called mobile channel. Mobile channel means in alluvial channels mostly during flooding they change their course, because the sediments through which they are passing through, it is loose and unconsolidated. So, that is why during flooding much chances are there. So, this river will change its course. It is very common in the Ganga plain rivers, it is very common in the coastal plain rivers which are flowing through the deltaic portions. So, during flooding they frequently change their course. So, that is why it is called mobile channel. This course is not intact. However, in contrary, if you compare it to this bedrock channels they are confined. They are confined course, because they are confined through hard rocks. It is very difficult to cut these hard rocks and migrate the channel from one place to another. So, that is why it is these alluvial channels are called mobile channels. So, as proposed by fixed channels in the bedrock can adjust to fluctuate the stream flow in many ways. Sediments that reaches a channel during intense runoff continues to move downstream until the stream power decreases. Much of this alluvium in the lower reaches of large modern rivers is relict deposit during the rise of sea level as most recent ice sheet is melted. For example, if you go to the deltaic portions where the river mouths in the nowadays whatever the river mouths are there. Suppose for example, if you take this east coast of India, we have many rivers where debouching to the Bay of Bengal. But if you analyze that river course, all those sediments now found in this river mouth are not the sediments which are deposited during the recent days by the river. Some of these sediments they are relict sediment means during sea level rise, during deglaciation. So, deglaciation means huge sediment was produced, or during glacier also during glacier movement huge sediment was produced and deposited along this coast. So, due to sea level rise these sediments are remain there, they are not able to move further downstream or further into the sea within these deep sea portions. So, that is why most of the sediment which is nowadays it is found along these river mouths, mostly they are relict sediment and few are these present day sediments. The relationship between this stream discharge, channel shape and sediment load and slope is known as hydraulic geometry. Hydraulic geometry, that means we have to establish a relationship between the stream discharge, then channel shape, then sediment load, then slope. So, that this hydraulic geometry, that means if we have high discharge and high sediment load, the higher slope, the stream shape will be different, stream behavior will be different. At a lower slope, low discharge is there or high discharge is there. So, that means these are the dependent parameters. If you change one parameter, the other will change automatically. So, this is called hydraulic geometry. Hydraulic geometry, that means if a channel shape is there, stream channel shape, what shape it will take, either it will be a meandering course, it will be a braided course, it will be a straight course, or the valley height its width ratio, how much will be the height to width ratio. So, all those factors that this is combinedly called it is hydraulic geometry, and this hydraulic geometry is dependent upon these factors. So, change one factor, the other will change automatically. So, they are the dependent variables. Now, we are talking about this longitudinal river profiles. So, this longitudinal river profile, the quality, that means longitudinal river profile, if you see here, this is the ideal longitudinal river profile, that is concave up. But as we are talking, within that concavity there should, if there is some convexity, some local convexity is there. So, that means it is the proportion, these portions are this interest for this geomorphologist to work out why this convexity is there. So, as the quantity of water in the channel increases, the downstream slope of this water surface decreases. So, as an empirical rule, slope is inverse function of discharge, higher slope lower discharge, lower slope higher discharge. So, water flows more efficiently in larger channels and therefore, requires less slope to maintain its velocity. So, this is the thumb rule. If we have higher discharge, then lower slopes, that means rivers which are at the lower slopes, they can discharge more water as compared to the higher slope. For effluent rivers, effluent means in the last class we are talking about the influent river and effluent rivers. So, effluent rivers, that means they are collecting water from this groundwater table, and influent they are going inside, gradually decreases this discharge decreases downstream, that is influence river, and this water amount increases downstream due to this contribution from this groundwater, that is called effluent rivers. With the discharge increases downstream, this long profile should be concave to the sky as parabolic curves. So, for alluvial channel that is well adjusted to the discharge and sediment load, the relationship between this slope S and mean annual discharge QM is as follows. So, this is for alluvial channel, that is valid for alluvial channels. So, slope S is equal to, it is mean annual discharge to the power minus 55. However, it is noted that many rivers have straight segments or even convex skyward segments as part of this overall concavity. Where in a experiment in Kansas, group of 79 rivers was taken, and which rivers mostly they transport coarse sediments. So, here the slope is equal to qm minus to the power minus 0.25, and that means the slope decreases only slightly as the discharge increases. So, that means here this discharge, this slope, they are interrelated, and that depends upon the which type of channels you are dealing with, what type of sediment it is transporting. Then another component of fluvial geomorphology and influence greatly to the fluvial geomorphology is the base level. So, whenever we say it is base level, that means it always comes in our mind that base level is the level through or beyond that or below which the river cannot erode, that is base level. Generally, in base level, once we say, always the sea level comes in our mind, or this sea level which is projected, it is a horizontal projection of sea level to this continent, that is called base level. But it is not always true. So, base level, once we say, that means there may be base level, or there are 2-3 base levels in a river profile, but one is permanent base level, which is true, which is the mostly the sea level, and other base level which is above this sea level, they are called local base levels. For example, a river which is passing through a lake, and then it is going down and again falling within this sea. So, this sea is the base level, but this lake is the local base level. So, if you compare this longitudinal profile of this type of rivers which is passing through many local base levels, you will find there are many convexity within that concavity. For example, if you see here, this is the sea level, and this is projected sea level, and that is called base level, and this is the longitudinal river profile. However, in this case too, this is sea level and this is a lake. So, this if you see this is the longitudinal river profile. So, difference is that here we are getting a local convexity, and this here once it is here it is a concave upward, this is concave upward, but here convex upward, but here if you see it is a steep gradient again. This is slow gradient is less, but here it is maintaining a steep gradient. So, that means at local base level, at the downstream of this local base level, either it is a lake or an artificial reservoir. So, these are called serve this local base level, and mostly this river creates small deltas at the downstream or this at the upstream or the upside of this reservoir, upstream of this reservoir, it is called a small deltas are formed. So, where river enters the sea, the gravity potential of this falling water reaches 0. No further conversion of potential energy to stream work is possible. So, sea level and its projection under this land is called ultimate base level of stream erosion. So, beyond which erosion is not possible. Most streams enter the sea with a considerable velocity, and therefore, the kinetic energy available to maintain their channel floors well below the sea level. But this observation does not invalidate that the use of sea level as the reference level for the limit of potential energy conversion. So, that means, though this sea level, though this river this has high velocity that can pass through this sea level and creates its own channel width is maintained, when channel depth is maintained, but still this sea level is called the, or it is considered as the base level, and it is assumed beyond which or below that level river cannot erode. So, if this type of artificial reservoirs or natural lakes are there within that river profile, there are also neak points, other local or temporary base levels such as dams, lakes that delay upstream erosion. So, this upstream erosion, it is a function of also base level. If base level increases, so the erosion capacity decreases. If base level decreases, the erosion capacity increases. For example, during this glacier time, when most of this waters they are in the glacier form, this base level was much below the present day. So, though there was no water, but at this time when this glacier melts and the rivers become activated, their erosional capacity is more, because the base level was much below. So, that the most of the sediments they are eroded and this valley widening takes place. Repeated continental glaciation during quaternary period introduced serious complication into the concept of base level control. So, that time base level fluctuation was there. Nowadays, whatever the base level is there, due to increase of sea level, the base level also increases. So, rivers erosional capacity and decreases, and sediment transporting capacity decreases. Dams on rivers impose an unusual form of local or temporary base level control. They trap the efficiency of a dam, and a large reservoir can exceed 99% of the sediment load. So, neither the Nile nor this Colorado now deliver sediment to this ocean, because most of these rivers are they are dammed. So, that the sediment is not transported to this local or the base level, and they are restricted. For example, if you for engineering geology, we prepare check dams before constructing a main dam or main reservoir. At the upstream end, we create check dams. If you see here, these are the check dams. So, the check dams are nothing. This main purpose of the check dam is to restrict or to arrest the sediment transportation. So, once we arrest sediment at the upstream end, less sediment is deposited, less sediment is contributed to the reservoir. So, that the reservoir life is expanded. So, that means, for longer reservoir life, we need to check, we need to construct check dams at the upstream, so that we can arrest the sediment movement to this reservoir. The adjustment of a river's long profile to a dam is generally flattening of this profile by deltaic deposition at the head of this reservoir, and steepening of this former profile by erosion immediately downstream of the dam. As we have already discussed, if you see here this river, if it is a terraces type occurrence, suppose we have lakes or whatever is there. So, that means, instead of the longitudinal profile like this, it is like this. So, here steep profiles are there, and steep profiles, longitudinal profiles, that will erode more. So, more erosion takes place at the downstream head of this reservoir, and more sediment is produced. So, that this longitudinal profile is very much important to know what type of river behavior, channel behavior will be, how much sediment will be produced, and what are the different what are the potential point where much sediment production is expected. Then another component, and the most important component of fluvial geomorphology, is the channel shape and solid load. So, we have different types of loads. One is solid load, another is this is dissolved load. Within that solid load, that means we have some tractions, some of the sediment they are transported within this river bed, some of these sediments they are transported by jumping, it is called saltation, and some of these finer particles, that is finer to finer particles, they remain suspended within this water, and as it is they are transported to this deep sea. So, they are suspension. So, apart from that, we have some dissolved salts, they are transported through solutions. So, solid load, once we say about these three components, that is this saltation, traction and suspension or suspended mode of sediment transport. So, depending upon this type of proportionate contribution of different size fractions, the shape of this channel vary. And second thing, that the shape of this channel throughout this geological time or throughout its lifetime of a channel, it does not remain constant. For example, if you see this figure here, this figure is taken from Bloom, and here the shape of this channel is, in the earlier time it was here. So, in the later time you see the shape of this channel was like this, again the shape of this channel like this, again the shape of this channel like this. So, that means I want to say, with time the channel shape changes, the height to width ratio changes. So, that does not mean the channel will always agrade, this is called channel aggradation. So, it may possible that this shape of this channel with geological time of or one flooding event or two flooding event or so. So, this channel will take this shape, we cannot deny it. So, that means I want to say the channel shape, whatever the shape we are discussing here, that does not remain constant throughout this geological time and throughout the lifespan of a channel. So, that means this how this channel will shape, how this channel, either it is asymmetrical or asymmetrical, it is will be that is meander or is a straight or braided, that depends upon the load of this system, how much sediment is transported. So, stream competency defines the composition of bed and bank of this river. Stream competency and stream capacity. Stream capacity means the total sediment it is transported by this river, it is stream capacity. Stream competency, how much size of sediment particle, what is the largest size of the sediment particle that a river can transport. So, that is stream competency. So, the stream competency defines the composition of the bed and bank of this river. So, what should be the bank and bed and bank shape. So, that depends upon the competency of this river, how larger particles, this how much larger particles this river can transport. If it is transporting very finer particles, then the shape will be different. If it is transporting coarser particles, the shape will be different. In the mixture of it, shape will be different, and either it will be a meandering course, it is a straight course, that also defined by this sediment transport or nature of the sediments. So, a constant exchange between bed and load takes place. So, because once we have confined system river, it is a confined system, two banks are confining the river, confining this water amount of water and water velocity or transportation system. So, here once it is transporting, the sediment is being transported through the river, it is always interacting with the bed, interacting with the bank and interacting with the water. Sometimes during swirling action, the sediments they are under suspension mode, it comes in the suspension mode. So, once it is reaching to a reach which is near about straight, or that will be the sediment that will move different ways. If it is in the meandering channel, it is passing through meandering channel, at the inner curve that will be deposit, at the outer curve there will be erosion. So, that means during the transportation of a sediment particles from this head of this river to this mouth of the river, it undergoes different type of transportation depending upon the river competency, depending upon the flood situation, depending upon the slope. So, that it is complete, that means it is a constant interaction between the sediment and this bank and bed, it takes place throughout its transportation. So, if channel is smooth or channel is rough, that also defines what type of a transportation will be there and what type of channel roughness, it is determined by the grain size or the bed form of this alluvial bed. So, if it is rough channel, it is, that means that depends upon the how much what is the larger size of the particle it is transporting. If it is a smooth channel, then probably it is clay size particle it is transporting. It is rough channel, boulder size particles it is transporting. So, that means I want to say the channel roughness, the channel shape, these channel properties, all those depends upon this what type of sediment is transported through this river and how it is interacting these sediments, this interacting with this bed and banks. So, I think we should stop here and in the next class we will talk about depending upon this sediment size, depending upon this interaction of these sediments with the bed and bank, how this channel shape is changing and how it is behaving or how it is influencing this channel flow and the stream capacity, stream competency and and how it is influencing our day to day life and our infrastructure development or any developmental project. So, thank you very much. We will meet in the next class.